intercalation of metal ions, right? And so just like lithium-ion batteries work on the principle of intercalation, these cavities have that propensity to intercalate ions into their systems and obviously have potential as battery materials as cathodes. So what I'm looking at in my work is exploring how the intercalation of these metals into these cavities, as you see, again, these individual cluster units come to make a larger 3D extended structure. So I'm looking at how we can synthesize these materials, have a bare phase, so they're thermodynamically unstable to synthesize directly. So you need to have a stabilizing cation, in this case copper, and then we take that cation out through an acid etch. We remove it. So we have a bare framework now, which is ideal for intercalation. So whatever metal we like to put in there, we can. And so what I'm looking at is in my research are changes as a function of one, the identity of the metal. So whether we use copper, lithium, aluminum, whatever it may be, and the amount that we intercalate into this system, how that causes actual changes as far as the structure and its behavior. And we are able to tunably control this enclosed structures, electro or photoelectrochemical properties, charge storage transfer properties, as well as magnetic properties and maybe even semiconductor properties. So there are a lot of things that we can control. And so I'm investigating as we change the amounts and identity of these metals, what that actually does to our system and how it can be applied to, at some point, battery synthesis, correct, or battery materials. This material has already been proven as the first functional multivalent cathode for magnesium. So magnesium intercalation, which would be 2 ions because it's a 2+ oxidation state. So instead of 1 ion carry or 1 electron carried by lithium, we would have 2 carried by magnesium. So it's very interesting in that regard. So this material is already been proven for that. So what I'm working to understand are more in-depth understanding of the kinetics and the changes and structural changes that occur as a function of intercalation. Let's see. Could you just finish?
Yes, of course.
Sorry, Kabian. Yes, ma'am.
I'm just asking for a friend. Can you explain what intercalation is?
Yeah, of course. I apologize. So if we go back.
Yes.
So intercalation would be the changing of the potential. So making it more favorable for this environment for the metal that was outside or in solution to inhabit. So it's something similar to in a battery where we have that spontaneous reaction going from the anode to the cathode, right? It's a process, but in this case, we make it more favorable. So we move those ions from the anode to the cathode and vice versa. So like in charging, it's the same principle as charging in a battery would be the intercalation where you sweep the potential to opposite. So I'll actually get into that in my next slide. If we go to the next one. Great question. So what are we actually doing? What does intercalation actually mean? So if you look at this, the summary of results here, we have a changing in potential from a maximum potential or more positive potential to a more negative potential, right? As we change that potential, we make the environment here more favorable for these metal ions to donate those electrons, right? So we want those electrons we want this environment to be more favorable. Each of these, so this is, firstly, these are the 3 analysis techniques that I'm using as far as electrochemistry to intercalate or incorporate my metals into my system. So in this case, we're looking at a cyclic voltamogram. So here we start at a potential of 0.3 and we sweep reductively, or we make the potential more negative, right? As we make it more negative, we make it more favorable for these metals to inhabit these cavities. And so we can look at changes as a function of controlling this potential and how that correlates to how many metals or how many equivalents of copper, in this case, we have, and how that changes our structure, okay? So each one of these reduction waves, I labeled them 1, 2, 3, and 4, are correlated to some electrochemical process. In this case, we correlate it to an intercalation, right? So this is a cyclic voltamogram where we intercalate, so we put the cations or the metals into the system, and as we sweep back towards our positive potential, you see an equal and opposite oxidative wave or an opposite wave that shows the de-intercalation. So they leave our system, equal, or it will be the equivalent to charging, right? So it's very interesting to see that we see this, firstly see this character, and then we can correlate that because of course we want to see what the system actually looks like with it in it. So right after 1, 2, 3, and 4, what our system looks like versus taking it back out. So to do that, we analyze it, and instead of sweeping from 0.3 volts, the positive to negative, and back, we leave it in the system, so we don't go back, so we stay reductive. And you see, I've correlated, Greg's covering a little bit, but that's great. I've correlated each of these peaks to resulting analysis. We call this XRD, so it's powder XRD, and we analyze the sample's crystal structure after to see what changes occur as a function of intercalating the different metals or incorporating these metals. So as we pass each one of these reduction waves, each one is a little bit of a stretch, but I have a paper coming out that will explain this in more detail. Each one of these reduction waves are correlated to an amount of copper in our system. As a function of that amount of copper in our system, we're looking at changes in our system and how we can control these changes and hopefully take these results and translate that to a larger system in multivalent batteries, multivalent cathodes, other materials, things of that nature. And you see a really cool trend. This is like trying to give a soundbite or just like a really clickbait kind of thing. This here is a difference as a function of intercalating 1, 2, and 3 coppers, and this black line is the original structure, right? So with no copper in it, you see that this pre-edge feature in our analysis is very pronounced, and it depreciates or it decreases in intensity as we intercalate more of those coppers. Okay, so this is a really, really, really cool finding because we see that as we intercalate, this is sulfur K-edge data for an X-ray analysis technique that we call ZANES. So we're looking at the pre-edge feature for the sulfurs around in the system. So as we intercalate more copper, okay, I'm really excited about this. Sorry. As we intercalate more of the metal into the system, you see a depression of this feature. And if we intercalate, because theoretically we can get a total of 4 coppers into our system, after we get that 4th one in, you should see a complete disappearance of this feature. This is a really cool finding because we can expand this to other metals. And as we incorporate other metals, we can use this data or this type of analysis to intrinsically track as we intercalate the metal or incorporate the metal, how it affects our different hosts, right? And so it's really, really cool. And it's really a really interesting finding to translate not to this system, but to a lot of other systems. And it'll hopefully set a benchmark for analysis techniques and being able to assess how, as you change your system's structure, how the electron donation actually can be monitored via this analysis technique. Okay, so that was a really cool finding. And I think that's the next one.
It's really neat, but here we go.
Okay, this is it. And so, yes, to summarize everything in a really, really quick manner, we've been able to successfully identify the copper intercalation potentials into the Chabrel phase host. We've been able to observe some really unique structural changes as a function of intercalant, so the amount of intercalant. I've also done some other intercalation work with different metals. And so my next steps I like to expand this work into directly multivalent elements. So I've already kind of delved into that a little bit. And I also want to start working on mixed metal compositions because this is something that's really cool because we can talk about kinetics, increase, movement of the metals in the system, right? Because that also correlates to how fast or slowly something charges or discharges as far as a battery goes. So these are really cool, really interesting future works that I would like to do, hopefully complete over the summer. And that'll be something very interesting and kind of taking the information that I've learned from copper and translating that to other metals. And I think with that, I think that's how the Velasquez lab is taking a bite out of today's energy problems.
Yeah, questions, please.
I know it's time. Fast.
I'm curious if you think this could be used to estimate the degradation of different battery chemistries.
Okay, so which part? Just the research in general?
I think I'm thinking specifically of the impact of the intercalation on the structure of the host, and if that has to do with how quickly the battery degrades.
So it does to a degree, but thankfully the Chabrel phase is a very robust system. So it is very stable, and that can be shown can be seen through cycles. So cycling, thankfully the Chabrel phase, like I said, is robust, but there are different techniques and ways that we analyze our samples that can check on the degradation and the stress that go in, because as a function of cycling, so how often you cycle, as well as lingering effects. So there are some effects like trapping, right? So you intercalate the metals just like lithium, right? You intercalate, and at some point, sometimes you get lithium trapped in the system that won't de-intercalate, which leads to overpotential, leads in a loss in performance. So there are a lot of things that we can take from our research and apply that to lifetime and degradation over time of batteries, and especially from the thermodynamic perspective. So we can look at stresses and strain on the actual structure and how that leads to degradation and correlates to degradation.
Cool.
And then instituting the Chauvel phase like in a solid cathode, do you think you'd need a liquid electrolyte, or do you think it could run solid?
So I'm looking at aqueous because ideally you want to do an aqueous electrolyte because you don't have as many problems with safety, as well as it's not as expensive. You don't have to worry about harmful byproducts, right? But it's not feasible for EVs and like small portable electronics, but it is feasible on the larger scale for grid, like demand shift applications. So that's why I kind of like this, because it's not as EV heavy application, but it is a larger picture application for as far as aqueous electrolyte. But there are several studies that do it in a very amount of electrolytes. So aqueous, non-aqueous, organic. Very cool. Yes, ma'am.
Could you talk a little bit about like what were some of the hurdles of like adding more and more copper to like your intercalation, and like what you expect is like the biggest hurdle in like adding that fourth potential one?
Okay. So Mark asked how does grass go slow? Okay, so the biggest hurdles, firstly, a lot of this data really came through trial and error and refining, because I would say it's you see a paper and it's like, oh, okay, yeah, I can just replicate that. It never works. It literally never does. So for me, what I realized is what is one of the biggest hurdles is plating, right? So we have this competing reaction of intercalating into our system, and then the potential, because of the electrolyte that we're in, the potential window starts to get a little closer to the potential to plate copper metal, because we reduced it so much. At some threshold, copper exists in a +1 oxidation state. So once we get too reductive, we start getting in the area where copper metal is more likely to plate on the surface of our electrode rather than intercalate into our system. And so it becomes a competing reaction between plating and intercalation. And that definitely is the biggest hurdle as far as getting copper forward in our system. And so a method to mitigate that is to switch from potentiometric analysis, where we're sweeping the potential from a positive to a negative and controlling current density at our surface based on surface area. So by limiting and controlling our surface area and controlling the current density as a result, we're able to mitigate plating a little bit more. And I've actually been doing work recently to get past copper 3 to get to copper 4, because there are a lot of interesting properties of copper 4, such as photoelectric properties, possible optic transitions from metal to semiconductor to metal band gap as far as the energy states and things. So there are a lot of interesting applications for that, but that is definitely the biggest hurdle, is the competing reaction between plating and intercalation. Gene, did you have a question?
I don't know, I think it was similar to Mark's question. Thanks.
I was just gonna say congrats on putting the paper out.
Almost there. So yeah, we're getting close. I would love to share that very, very soon. We're that'll hopefully go out on some email in the near future. It's finally out here. So yeah, thank you all for your attention, and I hope to talk more about it at some point. I'll pass it off now.
Thank you.
Thank you.
All right, next up is Alex. What I want to do is I want to see what this all looks like. All these little, what you're doing in the lab, Kabian, that's what I want to see. Let's see. Stop share. All right, we'll make it a clicker. You guys don't know this trick? Life lesson here. If you don't want your Microsoft PowerPoint to take up your whole screen, you hit browse by, you go to slideshow and hit browse by an individual window. I give this trick to people all the time, and that way, like if you're on your computer, you can have multiple things open without having it take up your whole, whoa, I blew your mind. I blew your mind. It's working now. I don't know. Maybe it has a distance thing. The battery's low.
Yeah, try finding some more battery. Sorry.
Alex charges.
All right.
All right, you are up, Alex. Go for it.
All right, awesome. Hey, everyone. Thanks for being here. Thanks to Ali and the EEI for inviting me in. So this is going to be very different than Kabian's. Not talking chemistry, and we're talking about cute little otters and floating solar. So, no, that's only partially true. So my name is Alex Cagle. I'm a fourth-year PhD candidate in the Energy Grad Group, and I work with Dr. Rebecca Hernandez in the Wild Energy Initiative. And I study land use in solar, specifically floating solar panels on human-made bodies of water. And the human-made part is a really important factor of this. And so this talk is on photovoltaics and UC Davis Arboretum. So improving water quality and then also using this as a techno-ecological synergy outreach project for educating undergrads and hopefully K-12 students. And this, just for reference, is Frank the Tank, the river otter that is at the site in Florida.
Not at UC Davis. Is it not working again?
No.
Okay, I'm on it.
Okay, thank you so
Yeah,
much.
you bet.
Okay, so a brief overview. First half, I'm going to go over my larger floating solar project. Kind of why are we mixing electricity and water, and then also what are the potential impacts or benefits, and what are the non-energy aspects that I'm exploring. And then also, why are we putting it on the Arboretum? So I'm talking about historical water quality at the Arboretum, opportunities for new experimental design, and then also public outreach and educational opportunities, which is something I'm really, really passionate and interested in. So first off, why are we mixing water and electricity, and specifically solar panels? So land use associated with the renewable energy transition is huge, and the expected increase in infrastructure for the US energy sector as a whole, not just solar, but this increase in renewables and then also transmission and distribution is estimated to be at 800,000 square kilometers by 2040. And so this is roughly the size of South Dakota. This is an obscene amount of land. And so solar PV and CSP, solar technologies, are relatively land intensive, but they're still viewed as land intensive. And so this creates tensions of land uses between agriculture, wildlife conservation, urban expansion. And this isn't necessary. We have a lot of built environments that we can utilize. And so there's also theoretical benefits for putting the solar panels themselves on top of human-made bodies of water. And this includes increased performance efficiencies through evaporative cooling mechanisms that occur under the panel, lowering the operating temperature. And there's also theoretical impacts to better the water quality by covering them in floating solar panels. So because they're on human-made bodies of water, typically we want them to be quote unquote sterile. So these are not wildlife conservation habitats. They're not areas where we want to see necessarily like a natural ecosystem. They're typically irrigation ponds, water treatment reservoirs. And so by covering them with these floating solar panels, you can potentially lower the water treatment costs by lowering algal growth. And a huge benefit is reduction in evaporation. So that's a major co-benefit we're looking at. And then also, as we were doing our preliminary studies for this cross-country investigation, we analyzed the amount of energy that was getting produced from the world's oldest floating solar, which is actually at a winery in Napa Valley, which is fantastic. It's one of our field sites, and found that per meter squared of installation area, so not per panel, but the actual installation area, it was generating 2.3 times more energy per square meter. So that's a combination of the array itself being more space limited and having that be a metric of focus, and also the evaporative cooling mechanisms. Next slide, please. Thank you. And so this is where my work pops in. Those are all the theoretical impacts. And so I'm looking at, are they accurate? Are they true? What's actually going on? So while floating solar panels, or FPV is the abbreviation I'm going to use, reduces direct radiation from the sun, there are, due to the tilt and the angle, there are hours of the day where sun actually penetrates and reaches the surface of the water. So this is huge for any photosynthetic activity. It's not a blank shade cover like the shade balls in California that you might have seen, or just a giant tarp or anything like that. And so that raises some questions. And then also, the floating solar itself shields the water body from wind interference and wind shearing. And so this dramatically lowers the amount of wind mixing of the water body, which naturally limits the algal growth. And the reason I threw this picture on top here is you can kind of see under each of these panels is essentially a little incubator where there's 18 inches of air and then there's water. If you can see directly under the panels, there's no wind. There's very, very little wind. And so this is another aspect to take into consideration. There's a lot of potential paradoxes between what we thought would happen and what could actually be happening. And also a lot of these water bodies are very nutrient rich. They have runoff from agricultural facilities, from natural urban areas. So those are some of the things we're looking at. And then also a lot of our colleagues are doing modeling efforts and kind of reiterating on lake models to see what would happen if you cover these water bodies and solar panels. But they're not taking into account the thermal properties of an operating solar panel. So they're operating as if it's just blank cover, as opposed to the fact that solar panels operate at a much higher temperature than the ambient air. So there's a lot of things going on, and we need some field data, and that's right. And so the main study, briefly going through, we have 4 locations across the country, one in Napa, one in Sonoma. The one in Walden, Colorado had to unfortunately be taken out last minute, and then 2 in the Orlando area. So we're doing a cross-country, cross-climatic zone kind of comparison here. And we're doing seasonal in situ monitoring of a lot of the major water quality parameters, and then also algal parameters, such as chlorophyll A and phycocyanin, optical pigments. And then we also, something I'm super proud of, we've gotten enough funding to put continuously monitoring water temperature and dissolved oxygen sensors. So you can kind of see in this figure up here. And so we're getting this really robust time series style data of what's actually going on at various depths in this water body. Yeah. Kate.
Under the in situ monitoring, what's the O?
Sorry, dissolved oxygen.
Gotcha.
Yep, that is the only jargon you'll get from me today. But yeah, that is dissolved oxygen. And so the reason we have dissolved oxygen water temperature as the long-term monitoring tools is everything else is super expensive, and you can also index some of these other water parameters to a certain extent with these physical properties of the water. And new hot take that we're starting up next quarter is we're also going to do some heavy metal analysis for the different chemicals that are different species that are in the panels themselves. We're working with the ICPMS Center, another jargon, inductively coupled plasma mass spectrometry.
Yeah.
So there we go. And so we're really excited about that, and that's going to hopefully also mold into a lab-based shop experience. And so quick little sneak peek on what we found here. So at one of the sites in Florida, we have a large covering of the pond itself with the floating solar panels, and it's about a 70% coverage, 30% exposed open water. And then there's a control pond with really similar metric properties and just sizing properties and influx of water. And so the red line is that control pond, and it's operating at, it has a lot higher temperature, both at the surface, which are the top 2 graphs, and at the benthos, the bottom 2 graphs. There's some other factors where we can't say that's statistically significant yet, but what is really interesting is on the top graph is when we break down this monthly data into a week, you can see the diel variations. And so the green is directly under the floating solar panels and the blue is in the open water body. And so we're seeing significantly different differences in daily maximum temperatures, and also a shift in when those daily maximum temperatures occur to later in the day. And so that's supporting the hypothesis that the panels themselves are actually creating a heat island under the panels in the water body. And that's something that's hasn't been discussed in the literature, and something that we're investigating further. And so it's a sneak peek. We have another year of data that we're collecting to make sure that this is true across all seasons and across different sites and different climatic bodies, but just a very interesting tidbit of the research going on. Okay, so that's the boring stuff. Why are we putting solar panels on the Arboretum itself? So this is a cross-collaborative project.
It works.
Awesome. And it's because, well, one, the water quality in the Arboretum is bad. It's not good. You should not be able to see translucent green from an aerial image. Like, that's not the best case scenario. And that's because of a bunch of different factors: slow flow rates, shallow depths of a concrete lined water body, nutrient loads from the water source. So it's not the best situation, but the better situation is we have an awesome water steward at UC Davis. Her name is Nina Suzuki, and she's really passionate about this. And the Arboretum is serving as this test bed for different water treatment technologies, but natural water treatment technologies. So we have floating vegetation islands, different aeration devices, and then also ways to also incorporate natural and native habitat for the local ecology. And so that's kind of how we got to choosing this. And so what I did was I was able to form some great connections with industry through my other project, and ended up partnering with Noria Energy to deploy this pilot demonstration and proof of concept study of a very small floating solar array on the Arboretum that runs an aerator to improve that water quality in the bottom portion of this subsect of the Arboretum. So this is the part down by the vet school. And so, like I said, small 5-panel, 2.1 kilowatt system, small inverter that powers a surface aeration device. But the kind of proof of concept here, and I'm not the electrical engineer, so grill me to a certain extent, and I probably won't know. But it's a closed circuit, it's not tied to the grid at all, and so it's operating as this essentially mini microgrid, and that's the whole proof of concept. And so it was really interesting because I'm a 4th year PhD in solar panels, and I've never hooked up a PV array before. And so I actually got to go out, see how floats are constructed, how they're attached, got to actually wire a full PV array, and then get in a little rowboat and go deploy this on the water body. And so as you can see, it's powering this beautiful surface aerator. It's not actually too beautiful and it causes a lot of muck, but this is kind of the whole installation phase, the whole partnering with industry, which is also something I thought was really interesting. And so what we're doing is we're following a similar experimental setup to what we're doing at the larger arrays, but focusing on how the aerator is affecting the water quality. So we have both upstream, so inflow is up at this far right corner, and then outflow is at that bottom left corner. And so we have water temperature and dissolved oxygen sensors upstream and downstream. The downstream location, we also have a multi-parameter SOM that's measuring some of those other water quality parameters like pH, conductivity, turbidity, and those algal indicators. But we also put a nitrate sensor on there so that we can actually see what's going on in the nutrient flow in the water body. And then under the array, we have water and light intensity sensors that we have kind of at chains on all 4 of those sites to see to what level is the light intensity actually reduced under the FPV itself. So that's the one application of this FPV installation that we're looking at. Otherwise, we're focused on what the aerator is doing to the water. And so what I'm really excited about is, and what Nori is excited about as well, which is even more surprising to me, is we're using it as an educational opportunity. So the Arboretum is fantastic in educating the public on what's going on in this waterway. And so we were able to work with their comms team to get these really cool signs put up kind of at all 3 corners around this portion, and a QR code that scans you straight to a blog. And so as the community is walking around and like, whoa, why are there solar panels on the water? They can just take a picture with their phone and see why we're doing this. And so that was really impactful to me, and I think it's something really interesting. And the ultimate goal is to upload periodically water quality data so that it's almost a citizen science-esque aspect of what's going on, and to have this really collaborative environment. And then also we're partnering with the Waterways Steward Internship Program, so that students are coming out and they're seeing what's going on, how this impacts water quality, and learning more about these techno-ecological synergies. And then also we're going to join up with a field hydro course in the fall to do pretty much the same thing and get exposure to environmental solar energy interaction, which is something I'm really, really passionate about. And then finally, the team and I have been applying to a lot of micro grants, like in that $500 to $1,000 range, to try to increase outreach to K-12 schools in the area. And so bring them out. The watershed or the waterway stewards already do a great job with kind of local engagement. So kind of picking into that network and showing not only what this specific project is, but solar panels are cool and renewable energy is cool and it plays a part in your local environment. And so kind of sowing that seed early for the possibilities within renewable energy. And so that is where we're at with this. And it's something I'm really excited to kind of share progress on as some of those items develop. So what's next in terms of the project itself, we're taking that proof of concept and plugging it into a giant multi-megawatt array, hopefully in the next year or so, pending funding, so that we can assess the actual impacts of the FPV, similar to my larger project, and then also impacts of the FPV with and without different water treatment technologies. So being able to plug in either aerators or some kind of UV treatment to this large generation array that is grid tied and has all these different capabilities in a way that still makes the water body self-sufficient and not needing to rely on external energy to filter or not filter, but clean its water with some kind of aeration device and keep the water quality up. And so that's kind of where we're going with this. And then in terms of the outreach, the pilot project is going to continue for 2 years, even after we have the proof of concept done, and hopefully flow more into this educational opportunity that the Waterway Steward program takes up definitely. And that's kind of ongoing. And then the water quality aspects of the pilot project are also going to be going on for 1 to 2 years and hopefully ongoing, which is hopefully less than 2 years. So just brief conclusions, water and solar panels are okay. They're really good for minimizing land use change for renewable energy transition. And also solar environmental interactions are really important. So understanding how large scale solar deployments impact whatever their local environment is a critical aspect of research that I don't think can be undersold here. And then also something that I learned through this is that pilot projects are a great way to expose your research and your project to the local community and also get younger researchers and young scientists kind of interested in what you're doing. And so with that, awesome. Thank you so much. And quick shout out. Have an amazing research assistant, Emil, who has helped with a lot of this. I want to thank Noria, Dr. Hernandez, specifically Nina Suzuki, who is the coolest waterway steward of all time. And so, yeah, thank you all so much.
Questions for Alex?
I have one question.
Yeah.
Let me pull it up.
Oh, maybe repeat, and if you could repeat the question, just, I don't know how good the Zoom,
Oh,
the
I can-
microphones are.
I can try to speak. So I'm wondering about controlling for efficiency decreases, so like dust and pollen, like underwater, is it similar to like mounted PV, as far as like, buildings and things? And how often do y'all service the photovoltaics?
Yeah, as in like watch the photovoltaics, yeah. So great question, and actually just brought on a whole new grad student to look at soiling aspects of water versus ground mounted solar. The answer is water mounted, water sited panels need a lot less servicing because of the natural increase of moisture in the air and the diurnal variations and dew and all that kind of thing. So they naturally clean themselves to an extent. There's a whole nother piece about how birds love floating solar panels. And that's another prong of that bigger research project, and they use it for hunting and they like just chill out and dry out there. River otters get them dirty. But so overall, they're less soiled with dust and pollen because of the moisture. But that is something we're looking into. And so like that data that I pulled to get that 2.3 times more generation was at a site that had a 300 kilowatt floating solar array. And then literally across a gravel road was another 350 kilowatt ground mounted array. And so it was a really good experimental design to do that. And yeah, we're finding that because land use is a metric that's taken into account for the FPV and the increased generation efficiency, it is a lot more space efficient at least. And so that's kind of the phrase I like using, land efficient or space efficient as opposed to the actual efficiency of the panel, because we're still about 6 months away from getting preliminary results on that project. Yeah.
Yeah, Alex, thanks for the presentation. My question is about the large scale photovoltaics projects. Do you envision those to be like connected to the transmission grid or more like microgrid level projects?
Yeah. So the question was, do larger FPV installations, will they be tied into a transmission network or more localized? And the answer is tied into the larger installations, definitely tied into a transmission network. So a lot of the pre-site considerations are distance from a transmission network. So that's why like the sitting reservoirs right behind hydroelectric dams is a really promising opportunity and a natural battery that I'm not going to go down the rabbit hole of. But because there are large enough human-made bodies of water, heavily human-altered bodies of water that can host 10 plus megawatt size systems, that a direct transmission tie is really critical. But on like these size, the large scale that we're working on, like the 2 to 4 megawatt, those are directly tied to the grid, but mostly supposed to direct power at that critical function of like the water treatment facility. And so there's a whole element of energy resiliency there that's also a consideration. Yeah.
Do you have a sense of the cost of floating panels compared to a ground mounted system?
Yeah, that's a really good question. And it's a lot more cost effective than you would think it would be. Like, I thought it would be a lot more expensive. And the only real thing, it's starting to hit economies of scale. It's around, the last I heard from the manufacturer is 10 to 15% more expensive from a mounting structure standpoint. But there's also very few float manufacturers in the world, and it's more of like a monopoly situation right now. And so as that expands, the costs are going to go down, and also they're so easy to put together. Like, they're literally just plastic puzzle pieces. And so as that technology develops, it should probably lead zero there.
I'm gonna raise my hand for Greg, who I think raised his hand.
Oh, great. Let's see. You can unmute yourself and ask a question if you'd like. Greg, are you there?
Yeah, I have a question.
Yeah.
When you're talking about water quality, you're talking about doing heavy metals testing.
Yeah.
Why? Like, what is the connection?
So heavy metal, trace metals specifically, that like cadmium, chromium, lead, different chemicals that are found in solar panels, even at very trace amounts in solar panels. Like, I'm very well aware there's not a lot going on there, but it's a consideration. And so the thought is, if we can test for it and show that there's nowhere near a direct correlation to an increase at any kind of public health limit, that's kind of like the goal of that observation. Because in Japan and some other Southeast Asian countries, there's been floating solar arrays that are put on bays or like lagoons and have had issues and got flipped over and just shattered all over the place. And so just kind of, I view it as reiterating the safety of this.
Okay.
If that makes sense. And
Gotcha.
that will be associated with a lab experiment where we shatter solar panels, put them in some water and see what happens.
Another question. I'm curious if finding an energy source for aeration is generally a challenge for irrigation ponds.
Yeah, so no, it's typically not an issue. And so the reason that this is like a proof of concept is more looking at, it's not hard to get energy, but it is an added cost for whatever the site is. And so it's an added benefit proposition for if you're putting an FPV installation on. The other part of this that I didn't mention was the whole point of this kind of Modbus setup is to clip the energy that would be clipped by the inverter before it gets clipped and sent out to the transmission line. So you're utilizing wasted energy from the site anyway. So there's another aspect there, but it's more of benefiting the water body. An additional benefit source for an FPV installation.
Okay, so that's just one co-benefit, but
Exactly.
the main reason someone would pay for it would be to get the power.
Yes. But the idea of a modular solar powered aerator is also like a different tangent you could go into, because getting aeration to like a stormwater runoff pond in Florida or something like that, where you have to grid tie it and dig under the pond and connect to an electricity source from a light pole or something is pretty time intensive and money intensive. And so there are applications, but that's not where this is. So it's a really good question.
That's super cool.
Yeah, really, both of you, amazing. So let's give them a round of applause. Thank you for joining us. We'll be back next week. We have two very different presentations again. We'll be hearing from a student and a staff member from the cooling center, one talking about ceiling buildings and the other talking about some testing of innovative kind of heating cooling technology. So come back next week. For those of you online, we hope to see you. Thanks for joining us and hope to see you soon.